Hello, my name is Vikram Jain, and this is my video presentation of Lab 2 of Physics 2211. In this lab, I shall explore the application of Newton's second law in a situation involving the motion of a falling object. The purpose of this lab thus had four components. 1. To observe an object's motion as it is dropped from rest at a certain height. 2. To create a computational model using Newton's second law, involving only gravity as an additional force. 3. To create another computational model in the same manner that takes into account both gravity and air resistance. And 4. To analyze how the contrast in these models highlight key aspects of motion where velocity is not constant. As we shall later see, the model with both air resistance and gravity was a much better fit to the path of the observed motion than my model with just gravity, proving that both of these forces have a big impact on a falling object's motion. For my experiment, I dropped an aluminum foil ball with a mass of 0.052 kg and a diameter of 0.06 meters from approximately 1.73 meters of vertical height as shown. Using the tracker application, I set the positive x-axis to the point to the right, the positive y-axis to point in the upward direction, and the origin to be set at the center of the aluminum foil ball at its initial position. As the nonlinear position versus time graph displays on tracker, the ball's velocity was clearly not constant during the video, suggesting that at least one additional force acted on the ball. This was a key element to take into account when creating the computational models with Newton's second law. As discussed in Lab 1, Newton's second law allows for quantitative analyses of dynamics, with its formula being final velocity equals initial velocity plus acceleration times delta t. Acceleration could be substituted in this formula by net force divided by mass, because force equals mass times acceleration. As noted briefly earlier, the next step in this process was creating a computational model using only gravity as my net force. In the Python code, the initial conditions were set in vector form as 0, 0, 0 for both the ball's initial velocity and position, because the ball began at rest. Because the ball fell vertically downward during the experiment, only the y component of the position, velocity, and force was needed to be taken into consideration, as we were only concerned with this aspect of the ball's motion. Delta t was set to be 0.001, so the motion of the ball and how it was affected by force could be seen more clearly. The acceleration of the graph of gravity on Earth is 9.8 meters per second squared, which was the value used for g in the code. G was a variable used in the code. The direction vector matches the way the axes were set up on tracker. In my loop, which continues until the final time in tracker, I calculated the weight force, which was the negative of the ball's mass times the constant g. The net force was equal to this in the first computational model, as gravity was the only force in this scenario. Then, the ball's velocity and position are updated using Newton's second law as shown. Running the code creates a graph that resembles the tracker graph. The second computational model took into account both the force due to gravity and that due to air resistance. The ball's mass, initial position, and velocity, delta t, and g all remain the same in this model. The air resistance constant needed for the drag force was found through trial and error by matching the ball's final position with the one given in tracker. In the loop, I added the calculation of the air resistance force, which was the constant from earlier, b, times the magnitude of the velocity squared. Adding this force to the weight force in the equation for Fnet had a significant effect on the resulting model. When the code was run, the air resistance clearly had taken effect as the object speeds up, as shown by the growth of the blue arrow. Again, this graph closely resembles the tracker graph. Finally, the experimental data, as well as my data from my two models, was compiled into a graph for comparison. And when this occurred, the difference between the two computational models was clear. The blue dots represent my observations, with the orange line representing my model without drag force, and the gray line representing my model with it. As you can see, both models were a good fit in the beginning, but as time passed, the gravity-only graph suggests that the ball should have fallen farther than it actually did. The model with air resistance is a much better fit for the end, although it too overstates the position of the ball during the middle of its motion span. Overall, the model with air resistance is clearly a better fit for the observed data in this scenario, showing that gravity isn't the only force that impacts a falling object's motion. Now it's time to address the what if and what does it mean portions of the post-lab discussion. Terminal velocity refers to when the forces of air resistance and gravity counteract each other so that the net force is zero, and thus the object has a constant velocity. In the model, with just gravity, we will never have terminal velocity because the velocity is changing with constant acceleration. In the model with air resistance and gravity, the object approaches terminal velocity but does not fall far enough for this to be reached. Had the ball had enough time to fall, it would have reached terminal velocity in the second model but not in the first. If the ball had been thrown downward, it would have had an initial velocity of less than 0. However, given the restraints that the ball had to fall, it still would not have reached terminal velocity in this scenario. It would go much farther than an object with 0 initial velocity initially and would reach terminal velocity faster. Thank you. That's all for my discussion, and I appreciate your time.